Welcome back to ECE 442-542. Just as a reminder, homework number 3 is due a week from Friday, and that's dealing with inverse Z transforms, which involves the region of convergence to obtain unique answers. Exam number 2 is actually 3 weeks from today, just as a reminder. Seems like we just had exam 1, which we did. It was a week ago, but our exams are roughly 4 weeks apart now. Today what I want to do is start with a quiz and see if your thumbs are working. These will be thumbs up, thumbs down, or sideways answers. Sideways thumb means this way. You could go either left or right. I don't care which way your thumb leans, left or right, but up and down, sideways. Those are the 3 answers I think we will be dealing with. We'll be talking about causality, whether the signals are bounded, whether it exhibits one of those characteristics, whether it has both of those or neither of those. So it could be non-causal, unbounded, might be a response. We'll then summarize our region of convergence diagrams. There's really only 3 patterns. They could be various sizes, but the patterns are just 3. You only have to remember 3. And from what we know about learning, maybe we can only keep 7 things in our brain at one time. Maybe I can only keep 1 or 2, but if you can keep 3, you can at least think of all 3 patterns for region of convergence. Then we'll talk about system stability and poles inside the unit circle, because some of these examples may actually illustrate where we can have poles outside the unit circle and still have bounded responses. And so there's maybe this conflict that you're having. Well, wait a minute. I thought boundedness or stability referred to poles inside the unit circle. And we'll try to make sure that that's clear when we talk about system stability, not just signals, but system stability and poles inside the unit circle. We'll make some observations after that or an observation with examples. And one thing I want to stress is that causality and boundedness are disconnected. They're not necessarily always the same. You can have a causal system that's bounded or a causal system that's unbounded, and you could have a non-causal system that's bounded and unbounded. They're not connected necessarily or always together or paired up. And ideally, we will start getting into discrete equivalence, which means how do we convert an analog transfer function, let's say g of s, into a g of z? How do we go from a g of s to a g of z, or a c of s to a c of z? We've already done that for a filter, I think. I remember talking about that earlier this semester. You've seen that discrete equivalent process. We'll now formalize it maybe today, maybe Monday. Region of convergence, the connections that we're looking for are when are the signals causal, non-causal, or two-sided, and when are they bounded and unbounded, and we'll do that now by means of quiz. I really think that you need to just sit and stare at that diagram for a while. That's just very well drawn compared to earlier drawings. But here is a z-plane. That's what we have. The blue shading is the region of convergence. And I'm asking you now, based on that diagram, do we have a thumbs up being causal, a thumbs down being non-causal, or two-sided, meaning thumbs sideways? Think for about 3 more seconds, and I'll say show your thumb on the count of 3. 1, 2, 3. Okay, most thumbs are in agreement and they're pointing up, which is consistent with a causal or n being greater than or equal to 0, and that's actually the correct answer. Now, keep that picture in mind and where that pole is located, and I want you to answer the following. Question 2. Is the signal response in the time domain for that pattern and pole bounded or unbounded? Again, I will give you a few more seconds to think about it, and then I will ask for a show of thumbs. Ready? The circle is this Jeopardy or question? Is the circle the unit circle? Is anybody else worried about that or concerned about that? I didn't label it, did I? It's not necessarily the unit circle. That circle that's bounding or bordering the region of convergence is not necessarily the unit circle, and the pole is right on the boundary. My drawing is not very accurate, but the pole bounds the region of convergence. Are we ready to answer? One, two, three. Who knows, right? We can't really tell. Until I label that pole, you don't know what we have. Is that true? Because you don't know whether that pole is inside the unit circle or outside the unit circle. It is interior to the region of convergence. If I now say, suppose A is less than 1, now show me your thumbs at the count of 3. 1, 2, 3. All right, now everybody, it is inside the unit circle, isn't it? And this is a causal, our signal is really looking something like A to the n for n greater than or equal to 0, and the only way that's going to be bounded is if A is less than 1. So we could do a question 3. With A greater than 1, and I hope it's clear. We just answered this, didn't we? So show of thumbs on the count of 3 if A is now greater than 1. 1, 2, 3. I just wanted to make sure you can go down with your thumb, right? You've been going up, now you're down. This is unbounded, isn't it? If we have A equal to 2, and we're raising 2 to higher and higher powers, we're obviously going unbounded. That's question 3. All right, let's look at a different region of convergence. Oh, and here is, let's say in a week's time you go, well, how do I remember whether this was causal or not causal? You can go back to your definition of the Z-transform and look at representative locations for Z that are inside the region of convergence and see which of these terms cannot be there. And in our case, we had a region of convergence that was going unbounded, going off to infinity. And if that's the case, we can't have these negative indexed time values being non-zero. All right, here's another. I'm still amazed at that picture. Although I'm not sure it's really a true circle, but anyway, it's better than what I usually draw. I spent a little time before class drawing that. Here is a picture, region of convergence. A, again, is bounding the region of convergence, if that's critical, and that's not even an issue necessarily for this first question, causality, non-causal, or two-sided. 1, so up, down, or sideways at the count of 3. 1, 2, 3. That was just the opposite of what we had before, wasn't it? Where we had the unbounded z. Now you could pick z equal to 0, and this should be down. With this same pattern, oh, I should move that over. But now a is bigger than 1. A is bigger than 1 with that pattern, up or down for bounded or unbounded at the count of 3. 1, 2, 3. See a few thumbs that are down, which now we have to remember we have a negative exponent. We have a signal that still looks like a to the n, don't we? That's the generic shape. Maybe it's scaled by something, but now n is less than 0. And if a is now bigger than 1, now that's downstairs with that negative exponent in a sense, and we're raising that denominator to larger and larger powers, and it's now collapsing. Meaning the correct thumb direction for that one was it. Which way were you guys pointing? Oh, you were pointing up? Oh, I got to talking about the people pointing down, didn't I? That's what threw me. You should have been. What happened? I'm not undoing anything. But there, how's that? Is that better? So it's outside the unit circle, which is what I was trying to argue. And up is indicating bounded. Now for a less than 1, is it clear what your thumb needs to be now? 1, 2, 3. Needs to be down, doesn't it? Now it is inside. Now it's 1/2, and you're raising that to a negative exponent. Now you're going unbounded with time for that particular shape, a raised to the n. Now we have an annular shape for our region of convergence. Bounded by 2 poles. We could have more poles less than A and more poles less or greater than B, but we're just worried about those bounding poles. Up, down, or sideways. 1, 2, 3. Annular means we're in both sides, don't we, in terms of our indices. This is now a two-sided sequence. Suppose A is bigger than 1, bounded or unbounded for your thumb at the count of 3. So A is bigger than 1, two-sided, 1, 2, 3. Most thumbs that are being shown are pointing down. Is that correct? Yes. Now A is, let's say, 2, And that one is actually, if you looked at the, you said it was two-sided. Now you can say that you have a to the n for n greater than 0 and b to the n for n less than 0. Now if a is bigger than 1, you have 2 that's going bigger and bigger with each added power of n, and so that will go unbounded with time. What about the next one? A is less than 1, B is less than 1. And again, we have this annular region. A is less than 1, B is less than 1. 1, 2, 3. It's likewise unbounded, isn't it? Now we have something that's 1/3 or 3/4 to a negative exponent. That's going to grow with time. One more. A is less than 1, B is bigger than 1. 1, 2, 3. Now you have the unit circle inside your region of convergence. You now have a bounded sequence. Is that clear? Are you comfortable now with these diagrams? We really have only 3 patterns to worry about. With this pattern, what's our behavior? Is it causal, anti-causal, or two-sided for this pattern? Irrespective of where A is, right? Independent of A, this you can now say is causal. Pattern 2, now you pick a convenient value for Z, maybe at the origin, and you plug that into your expansion, your infinite series expansion, and you see that those negative exponents that deal with right-sided sequences, you shouldn't have any of those. This now says that for this pattern, you're looking at non-causal, whether A is less or larger than 1. It doesn't matter. It's still non-causal. This one, now you have the region of convergence outside one pole and inside another. That gives you your two-sided behavior. And those are now your 3 patterns that you need to know. And you can determine causality just from the pattern. Stability is a different question, isn't it? That depends on where those poles are located relative to the unit circle. Now, let's talk about system stability. Yes, question. I have 3 patterns. So what's the other pattern? Okay, so you're wanting to have a missing donut. You want the entire Z-plane, but you're going to erase an annular shape in that. You can't have a region of convergence that's disconnected, meaning that would have something that's maybe Z equal to 1/4 and maybe Z equal to 3. And with a gap between. You can't have gaps in your region of convergence. Your region of convergence needs to be connected in a mathematical sense. You can't have gaps. You can't. So I think the question was, why can't we have that? Is that the question? And my answer is this: you can't, you're not remaining in the region of convergence if you go from point A to point B. And you need to be connected with your region of convergence. Your region of convergence can't leave the region of convergence to go to another point in the region of convergence. Your region of convergence needs to be connected, so this is not a valid region of convergence pattern. Does that help answer your question? And with this last pattern, with the annular shape, no matter what A and B are, you can still have an annular pattern. And you could have many, many different poles, meaning you could have more poles here, or you could have poles here, and that pattern is still okay. Is that clear? But where can you not have poles? Relative to the region of convergence. You can't have them lying inside the region of convergence. You can't have poles there. That's not going to happen. Other questions on these patterns and why we really just have three? Moving on then to system stability, and maybe this idea of, wait a minute, you've just shown that you can have a pole, let's say at B, which is at 2, and that gives you a bounded answer, doesn't it? A bounded response when B is at 2. Well, that seems to be disconnected from having a stable system with poles inside the unit circle. What's the disconnect, or what's going on here? That's what I'm trying to explain here. One is, this is a controls class, and we're going to then say that for stability, we want poles to be inside the unit circle. We put on our 2-year-old hat and we ask why, and we say, here's a system. We're going to be dealing with a system. That's the green box. We excite it, and the response occurs after the excitation. We don't have systems that get excited or shake before they get hit, or shake before they get excited. Is that clear? So we are dealing with systems that are causal. We might have signals that are non-causal, two-sided. So when we're talking about signals, that's when we can have poles that are outside the unit circle and still give us bounded answers. But for systems, our systems in a control setting will be causal. We kick them and then they move. They don't move before we kick them. So we excite them, we get the response after the excitation. That means we have a causal system, which means now our region of convergence is consistent with a causal time domain response, which means that it's always outside the outermost pole, which says now I do have the unit circle drawn on this diagram. It's the one that's in red, and for our systems to be stable, we need all of those poles inside the unit circle. We can still have Z transforms that have poles outside the unit circle for a causal system. It will be an unstable system. That's okay. Then we'll have to stabilize the system with a controller. But for stability, we want to put all of those poles inside the unit circle. The closed loop poles, if our open loop poles are not there initially. Is that clear? And is it the reasoning behind why we're talking about stability, having poles inside the unit circle, and why just a few minutes ago we had poles outside the unit circle that were giving us bounded signals? Those are consistent concepts because in this system, we are forcing it to be a causal system. And because of that, that forces this pattern on us with our region of convergence. It's always outside the largest pole. And that's because we pick this region of convergence, or this region of convergence is defined to give us bounded infinite sums. That's how we pick the region of convergence, or we define it. So let's see if we can think about what we've just talked about relative to the following observation. And that is that signal causality and bounded time response let's say the behavior of the bounded time response are two separate characteristics. Meaning we can have a signal can be causal, which means it's defined for n greater than or equal to 0, or it has non-zero terms for n non-negative. What's our region of convergence for a causal signal? Is it inside all the poles or outside all the poles if it's causal? Here we have that expanding region of convergence. The region of convergence is external to all poles. So we can have a signal that's causal, yet its time domain response might be unbounded, which means where are the poles relative to the unit circle? And how many poles does it take for a system to be unstable? If I have a system that's 10th order, do I need 9 unstable poles for my system to be unstable? Do I need 8? I only need 1 bad apple, don't I? 1 bad pole, where bad is it has something outside the unit circle, would cause our signal eventually to go unbounded. Can you come up with a time domain waveform that illustrates that? What would be an h sub 1 of n that's causal yet unbounded? And it's not that difficult, I hope. If it's causal, we know that. And if it's unbounded, then we can just make something bigger than 1, let's say 5, raise that to the nth power. That's now an unbounded waveform that's causal. And what's its pole 0 diagram look like in the z-plane? And its region of convergence. Does this signal have a z-transform? This is r to the n. R can be any number, can't it? and it has a z transform, z over z minus r. That's fine. R can be bigger than 1 and it still has a z transform. But what's the pole zero pattern look like for this signal? Where's the pole going to be? If you took the z transform of this, where's the pole? It's at 5, isn't it? And our region of convergence is all of those values in the z-plane that have a magnitude bigger than 5 will allow that z transform to exist. Did everyone come up with that example or an example similar? All you needed was that number that's raised to the nth power to be bigger than 1 and n to be non-negative, and you would have a causal unbounded waveform. There's a flip side. We can likewise have a signal, or a signal can be non-causal, which now says that n is negative, the time index. Where's the region of convergence? Do you see where the region of convergence is for a non-causal signal? Is it exterior or interior to the poles if it's non-causal? Now it's interior, isn't it? We can have a non-causal signal that is unbounded. Do you see the picture mentally that's going to produce such an example? If I now ask you to draw the picture for this in the z-plane, what's that going to look like, and what would be, let's say, h sub 2 of n? I'll do the hard part. We just said that it was non-causal, so I know n is less than 0. And I'll even do this. What's inside the argument of that exponential? We now have non-causal, unbounded. Do you see the picture in the z-plane and what's in that argument of h sub 2 of n? Anything less than 1 will be fine, won't it? And to make it easy, we can make it real. We can make it 3/4. We could make it minus 3/4 if we wanted. We could make it minus 1/2. That's fine. It's going to go unbounded. Here we have 3/4, and our region of convergence is there, and our picture in the time domain looks something like that, where this is now the reciprocal of 3/4, which is 4/3, and then this is 16/9. Now 16 times 4 and 9 times 3, so it's going unbounded as n goes to smaller and smaller values. That's what it looks like in the time domain. This is what it looks like in the z-plane picture diagram. And we can have the other two cases. These two cases were both unbounded, weren't they? In this case, we need for z to be unbounded. Well, maybe I should go the other direction. To be unbounded, we needed the poles inside the unit circle. For this non-causal example, here was an unbounded causal example, and we can have the other two cases. We can have a causal sequence that is stable. What's h sub 3 of n look like here? What's an example? If it's causal, we know we have that pattern. Ooh, that's not even centered on the origin, but you can make yours centered on the origin. And our pole, let's say, is right there. Maybe it's 1, 4. And finally, for these two patterns that I'm dealing with, we can have a non-causal sequence that's stable. What's that look like? If it's non-causal, we now know the region of convergence looks like this, and poles can't be inside the region of convergence. So let's say a pole was bounding that region of convergence. This pole, in order to give us a bounded sequence, or a state, maybe I should say, that is bounded, I'm going to try to reserve stable and unstable when I'm talking about systems. Signals, I'm going to try to use bounded. If this is bounded, what do we know needs to go in the argument of our exponent? Where is that x? And what is it relative to? It now needs to be bigger than 1, doesn't it, in order to make this sequence bounded. So we could say 6 if we wanted to. Questions on that? Yes? Which one? This one? What about it? So the values are getting smaller as they approach 0 in n, but as n gets more and more negative, you now have 3/4 to the minus 1, which is 4/3. Then you take 3/4 to the minus 2. So take 1 over 3/4 squared. And you should get 16 over 9 at minus 2 for n. Is that making sense? So it should be getting bigger as n gets more and more negative. And you'll want to go home and think that through if it's not making sense now, and then correct me in my office hours or some time later if that's not correct, if I'm not seeing. Am I not seeing that right? Is that okay? Other questions on these four cases? Those four cases are causal, bounded and unbounded, anti-causal, bounded and unbounded, and you could also have two-sided, bounded and unbounded. When would you have an annular region of convergence that gives you bounded waveforms? As long as that annular region, as long as the donut contains the unit circle, that shaded area in the donut or the annular region, as long as the unit circle lies in that, you're going to have bounded waveforms. Questions on that? Now that we have that background, the reason we're spending so much time on region of convergence and frequency domain and time domain is so that we can now talk uniquely about inverse Z transforms. Remember when I was motivating this region of convergence, I maybe said, is it possible to tell what f of n is given capital F of Z? To find a unique let's say, to find a unique inverse, let's say, x of n, we not only need to know the transform, capital X of Z, but we also need to be told what is the region of convergence. If nobody tells us what the region of convergence is, then we could have multiple answers. The inverse could be different between two different people. If I give you a pole or a Z transform, Z over Z minus 1/2, and tell you and ask you to find little x of n, you have to say, well, I'm going to assume the region of convergence is here or here in order to make a unique little x of n. Because you could have a causal or you could have an anti-causal sequence corresponding to Z over Z minus 1/2. Let's look at an example. Suppose capital X of Z is Z over Z minus 1/4 and Z minus 2. And without me giving you a region of convergence, do you see how you could make that have all sorts of different waveforms in the time domain based on our three different patterns? We could have one pattern that the region of convergence is outside or exterior to all poles or those two poles. Would your system have a bounded response if that was the case? Maybe I'm getting ahead of myself. Do you see what I'm trying to ask? You have two poles in your z-plane. Now if you had the region of convergence given to you that said it's exterior to those two poles, what kind of waveform modes do you have? Or what are the waveform modes, or how are they given to you? You can really start looking at many different questions based on just given this, but let me say that for this example, let's have a region of convergence. I could give you three different possibilities. Let's just go with one. Let's say that Z is now an annular region. It's bigger than 1/4, the region of convergence, and less than 2. Here are some possible questions that you could even ask before or answer if you were looking for partial credit without even finding little x of n explicitly. You could say, where are the poles located? And I hope you can tell me where that is based on that capital X of Z. We now know, based on all of your preliminary or previous coursework, what poles are. Those are the values of Z that cause the denominator to vanish. And you know what those are by this factored form of the denominator. We have a pole at 1/4, and we have a pole at 2. Here's another question. So we now know, well, I'm getting ahead of myself. Is x of n one-sided or two-sided? And what allows you to make that answer or to provide an answer? Maybe I need a show of fingers. Is it 1 or 2? One-sided or two-sided? 1, 2, 3. Okay, it's 2, isn't it? Because it's annular. So this is now two-sided because of the region of convergence. It didn't matter what capital X of Z was necessarily. We needed to know what the region of convergence was to provide this one-sided or two-sided. The annular region of convergence now says that it's, or implies that we have a two-sided waveform. What's the structure, as another question, of little x of n? And this is an exam 1 question, isn't it? I gave you that capital X of Z. Could you now tell me what is the time domain structure of little x of n? What are the modes? Or what are producing our structure for little x of n? And you tell me where to stop. Maybe we should stay on the example. But it's staring us in many different places, isn't it? What are you looking at for the modes of your response? The answer to question 1 or the denominator of your transfer function should be enough. We now have a mode at 1/4 and a mode at 2, which now says that we have 1/4 to the n and 2 to the n. Do we know anything more about that structure? Are they both active? You said it was two-sided, the response. Is this little n positive and negative for both 1/4 and 2? And how do we determine that? Which one is which if they are not both positive and negative signs on the exponents? Did everyone hear that? Spoken with authority answer. 1/4 corresponds to non-negative indices. Is that what I heard? Not really. I heard positive, right? I think. My hearing's not very... The comment was that this term is that. Is that true? And why do we say that? How can we know that relative to this given information? That pole is interior to the region of convergence. The region of convergence for that pole is exterior to 1/4, and that's the causal pole or poles. If they are interior to our region of convergence, this now says that this region of convergence is exterior to that pole. Now, what do we know about 2, the mode 2? Just the opposite, right? That's the non-causal one. That's because, so this region of convergence being exterior to that pole tells us it's causal, and here for the 2, the region of convergence is interior to this pole, which says that it's anti-causal, that particular mode. Is X of n a bounded sequence? And you can get this multiple ways, can't you? You can sketch the z-plane region of convergence and then see where that is relative to the unit circle. And here you're looking for the unit circle being inside the region of convergence, which it is, since the region of convergence is bounded by 1/4 and 2. Or you could now look at this time domain expression or response and say 1/4 to the n is collapsing, and 2 to the n with n negative is also collapsing. X of n is a bounded sequence. Since the region of convergence contains the unit circle. We can answer those questions without even explicitly finding little x of n, can't we? We know a lot about that signal just by looking at capital X of z, the poles in the region of convergence. That tells us a lot. Now let's figure out how to find the actual little x of n for that capital X of z. And what we need to realize is that we need to split X of z effectively into 2 pieces. To yield the 2-sided little x of n. We know that we have 1/4 to the n being true for n non-negative, and we know that we have 2 to the n for n negative. How are we going to find little x of n? What do we know about Z-transform tables? Can we use those for this case? Can we use that expensive calculator mom and dad or somebody purchased for you? Yes, let's go back to our partial fraction expansion. And what's the strategy or the process for finding matching pairs in the Z-transform table when we're doing inverse Z-transforms? Do we partial fraction expand x of z, capital X of z, directly? If we don't, what do we work with? Do you remember what we talked about last time? We want to force eventually a z in the numerator of our expansion, and to do that we trick our partial fraction expansion process into forcing that z in the numerator by factoring capital X of z over z, which says that we now have 1 over z minus 1/4 and z minus 2, which we can now partial fraction expand into, let's say, an a and a b partial fraction expansion coefficients. And now we find a and b like we've done traditionally using this particular piece of the expression or equation. We can now multiply both sides through by the factor, let's say, z minus 1/4 to find a, leaving us on the left 1 over z minus 2, and we evaluate at z equal to 1/4. We know now that a is minus 4/7, and b can be found similarly if we multiply both sides through by the factor underneath the b term, which is z minus 2, leaving us with z minus 1/4. We evaluate that at z equal to 2. And b becomes 4/7. We now have our partial fraction expansion that we need. If we multiply both terms back by the z, we have minus 4/7 z over z minus 1/4 plus 4/7 z over z minus 2. And we can think of this now as x, capital X sub 1 of z and capital X sub 2 of z, and we can find those in the Z-transform tables. And that allows us now to conclude that what's little x1 of n? Do you remember your tables? You know the structure, and you've just found the fraction of that that's present, or the multiple of that that's present. It's now minus 4/7, and 1/4 corresponded to the causal piece. This is now for n greater than or equal to 0. Little x sub 2 of n had a scaling of 4/7. It was 2 to the n, and that was the non-causal piece. And we could write this many different ways. One thing that we might start getting used to, and I will probably use this multiple ways, but we could talk about the unit step in the discrete time case, meaning 1 for n greater than or equal to 0, and 0 for, yeah, that's right. I was, for some reason, thinking about the unit pulse. The unit pulse, I don't know what notation I will use, but that's 1 when n is only equal to 0. It's now no longer an impulse, it's a unit pulse for a discrete time. This is now a unit step. It has a value of 1 when the argument is always non-negative, and we can use that to write down an expression for x of n, one expression that incorporates these two separate pieces for different time indices. We could say that we have minus 4/7, 1/4 n, u of n. That's true. That's only going to be present for non-negative n's. Now we need to add in the next piece. And what do we put in there? If we put in minus n, what happens? Then at 0, that's going to be on also, isn't it? And we don't want it on at 0, do we? We only want it on for minus 1, minus 2, minus 3. And we can make that happen if we just modify that argument ever so slightly and say something like that. Now at n equal to 0, what's happening to the argument? It's u of minus 1, which it's off, which we want it off at 0. At n equal to minus 1, what is it? U of minus a minus 1, so that's u of 1 minus 1, that's u of 0, that's now turned on, and for all negative indices less than minus 1, it's going to be on. Is it clear why that's equivalent to the earlier two-part answer for x of n? Now you can write it as one expression. You just need to watch what's going on. You don't want to double count or include both pieces at n equals 0, and we avoided that by making sure that our argument made sense on that unit step that was waiting, turning it. Here I'm using the unit step as a switch. The leftmost unit step is a switch for non-negative n. The rightmost unit switch is unit step is a switch for negative n. Or you could have written your answer as x of n is equal to minus 4/7, 1/4 to the n greater than or equal to 0, or 4/7, 2 to the n less than 0. Those are equivalent expressions for that waveform, that response. And that's the inverse Z transform of capital X of Z. Do you see what would have happened if we would have had a different region of convergence? If I had a region of convergence that was interior to 1/4, what kind of a waveform would I have? One-sided or two-sided? 1, 2, 3. Oh, show me your finger when I count to 3. So now I'm waking you up. We have the capital X of Z that we started with, wherever that was. Wow, really? There's capital X of Z. Don't think of that region of convergence. I've now changed the region of convergence to be interior to 1/4. Is the signal waveform in the time domain, one-sided or two-sided. Show of fingers at the count of 3. 1, 2, 3. It's 1, isn't it? We have something that's not annular, so that tells us 1. What kind of a waveform is it? Causal or non-causal? And if you don't remember, just go back to the definition and look at a nice value or a convenient value for z. This will be causal, non-causal. Non-causal. Do you see the other pattern that we could inject here? We could say, oh, a region of convergence beyond both poles. Then it would be one-sided causal. Would it be bounded? No. Would the earlier example that we had, interior to 1/4, would that be bounded? That non-causal. Bounded or unbounded? Bounded is up, unbounded is down. Show of finger or thumbs. 1, 2, 3. Trying to keep a lot in our head, aren't I? We had an interior. Where was the unit circle relative to that disk? That disk was only of size 1/4 in radius, wasn't it? It's not enclosing the unit circle. That should have been an unbounded waveform. Questions on these examples, or region of convergence, inverse Z transforms, how to find these connections. Causality and boundedness are separate. Region of convergence determines when you have that Z transform defined, what values of Z. Allow that Z transform to be a bounded number or a well-behaved expression. I didn't see any, or hear, I didn't see any questions. I didn't hear any questions, see any hands, hear any questions. So we're going to move on to the next topic, which is discrete equivalence. Here we are trying to convert analog transfer functions, which might be a filter, which I might call H of S. It might be a controller, which I might call C of S. Or it might be a plant. A plant is, well, it is green there in writing, but this is a plant that's maybe a dynamic system. It might be a circuit. It might be a mechanical system. It might be an electromechanical system. That's our plant. That's G of S, and we're supposedly familiar with the G of S. We want to now take that into a discrete time system, or a discrete time filter, or a discrete time controller, which we will then call H of Z, C of Z, and G of Z. Or if you remember some of your earlier assignments, maybe you're curious what's going on behind the scenes of this MATLAB function C number 2D. C to D, continuous to discrete, is where that's coming from. They get very creative when they name these functions, don't they? Well, it saves in typing. We're engineers, we don't like to type too much, so just C to D, and now we have something in the argument. We want to go continuous to discrete, and we can do that many different ways. If you do a help C to D in MATLAB, it's going to give you a lot of information. There's a lot of different ways to go continuous to discrete. And that's what we're going to try to learn now, is how we can make that happen. Here is our, wow, a little bit large block diagram for a continuous time control system. This was on your first homework assignment, wasn't it? Where I was having you find transfer functions between these different signals. Typically, we concentrate on the reference input to the output, but you might have a disturbance D. That might be you're out in the ocean in a sailboat and you have a disturbance wind coming at your sailboat or sail, or maybe you're going up an incline in an automobile and that's now a disturbance. Maybe it's something that's disturbing the shaft on your motor that's spinning. You have a disturbance. You might even have noise in your measured signal before it gets fed back. Whoops. Typically, this will be negative feedback, so I'll put a minus sign there. And we may or may not have dynamics in the feedback path. H of S may be unity. We may just have a straight line. But this is the diagram you might have seen in an earlier class. You may have seen it in homework 1. Now what we want to do is figure out, when do we change maybe this to a digital representation, or when do we change this to a digital representation? And we can use different techniques for going continuous to discrete depending on whether we're dealing with G or C. That's the idea that we're wanting to cover. There's two main situations when we might want to go C to D, and that's what I just highlighted. One was blue and one was yellow. Don't ask me which was which, but we'll clear that up as we go. One way that one of the situations or reasons might be if we have a filter. We've done a low-pass filter already in class. We had a C of S. You could now write down an analog filter with an R and a C. You now want to know, how can I do the same filtering in Excel or with some difference equations? How can I filter this signal, this waveform that maybe somebody has given me, and I don't want to go build a circuit and experiment in the lab. I don't want to create that signal in the lab and have to measure that analog or continuous waveform. We may want to then convert C of S to a C of Z. C of Z will allow us to now cross-multiply and generate a difference equation. And then we simply number crunch or put it into Excel. That's one way that we might want to, or one reason for going continuous to discrete. The other reason is if we have a plant, an electric circuit, a mechanical system, an electromechanical system, a hydraulic system, we have a G of S. And we want to maybe control that digitally, or we want to analyze it digitally. We want to now find the G of Z corresponding to that G of S. There's two different reasons, two different situations, two different scenarios that we usually are confronting in this class to worry about C to D. Here is reason one. Wow, let me get it even smaller. Here's reason one, and this is for converting maybe the controller, C of S, to a C of Z. We may want to not have an analog controller. We want to control our system with a digital controller, a microcontroller, maybe a computer, maybe a microprocessor, but we want to put that microprocessor where that capital C of Z is. So we need to find a difference equation and not Josie's R's, L's, and C's or op amps. We want to replace all of that with just a difference equation. That's reason one. So we want C of Z, the digital version, to be a discrete equivalent of what we've already, maybe somebody gave us an analog controller. The second reason is now what you were looking at when we were dealing with studying for exam 1, and you kept seeing this ZOH, zero order hold equivalent. Now we want to replace the analog plant together with the hold device and this sampler. We'll pull all of those together to create another discrete equivalent, meaning our discrete equivalent will incorporate the D to A and the A to D. The hold device and the sampler will put all of those packages around the plant and generate a G of Z so that we can get rid of all of those and just have a G of Z in our diagram or in our analysis or in our design. Those are the two reasons, situations that we want to worry about. We will start next time learning how to take G of S to G of Z.